Welcome to section 6.2, part 2. And this time we're going to kind of go the other way. We're going to be given a probability or a percentage. We're going to figure out the cutoff values. So suppose that the number of French fries in the batches at In-N-Out Burger are normally distributed with a mean of 42 French fries and a standard deviation of 3.7 French fries. How many French fries would be in the container if your French fry basket was in the 96th percentile for French fries? All right, so let's go ahead and attack this problem. Let's use Desmos. So let's open that up again. And here it is, normally distributed with a mean of 42 and a standard deviation of 3.7. So one thing we could do, and I kind of already have the answer in here because I was messing around with it. One thing we can do is we could just like guess, right? Let's guess 45 French fries. So if we had 45 or fewer, the probability of having 45 French fries in your basket or fewer is 0.79%. So it's like the 80th percentile would be 45 French fries. That's not quite enough. Let's go up to 48 French fries. Well, that's the 94.7th percentile. So not quite. 49 French fries, we cross over and we would know that we'd be above the 96th percentile if we had 49 French fries. Well, if this was a problem that had a little more options, a larger values, it would be pretty boring and tedious to have to just guess and check over and over again. Luckily, you don't need to do that with Desmos. There's another function we can use. So the function we're going to use to do this is called inverse CDF. And this is the inverse of a cumulative probability distribution function. That's what the CDF stands for. And so the first thing you have to tell this function is what type of distribution. Is it uniform? Is it exponential? Is it binomial? Whatever. Well, that wouldn't be a binomial, but it's normal, right? So we're going to go normal distribution. I can't spell normal. That will be helpful to spell that correct. RMAL, normal distribution. And our mean is 42, and our standard deviation is 3.7. You always have to tell that about your normal distribution, comma, and now you put in the percentile you're interested in. I'm interested in the 96, so 0.96. And it tells me the value in the 96th percentile is 48.477753, blah, blah, blah. And actually, if I come up here and I put that in for my max, if I put in 48.477538, you can see it's getting closer and closer to 0.96, and it will get as close as we need it to get, 636. Okay, whatever. You guys see how to do that. So inverse CDF, you put in the name of your distribution, or in this case, normal distribution with the mean and the standard deviation. And then the final part here is the percentile that you're interested in. This tells us it's 48.4. So let's go back to our distribution. It tells us 48. Oh, well, this one turned out. What do I have slightly different? Oh, well, it's close enough. 48 French fries is our answer. Whoop, 48 French fries. All right, let's try another problem with this. So in the United States, the ages 13 to 55 plus of smartphone users approximately follow a normal distribution with approximate mean and standard deviation of 36.9 and 13.9, respectively. Find the 80th percentile of this distribution and interpret it in a complete sentence. So I would like you to pause the video right now, go to Desmos, find the 80th percentile for this new this new normal distribution, and then come back and interpret the 80th percentile. I can't talk today. 30 seconds. All right, are you back? Let's go to Desmos and do this together. Yeah, sure. Going to Desmos, and instead of, I don't really need this, I'm just going to close that. Inverse normal, and I'm going to do 36.9. And my standard deviation is 13.9. But this time I want the 80th percentile. And I get 48.5985. So 48.6 years is the 80th percentile. All right, the 80th percentile is 48.6 years. And that means that 80% of smartphone users are in the age range 13 to 55 or 48.6 years old or less. That's what the 80th percentile means. 20% are going to be older than 48.6 years. All right. We're going to talk a little bit about z-scores. Z-scores were something we had to use a lot back in the day when we didn't have good computers. We don't use them as much anymore because Desmos can help us do our calculations for probability quite handily. But what we can do with z-scores is z-scores tell you how many standard deviations you are away from the mean for a particular data point. So let's just say we had a normal distribution. It has a mean of 5 and a standard deviation of 2. If we look at the value 11, we know that it's 3 standard deviations above or to the right of the mean. And we know that because if you take 5, that's my mean, and add 2 3 times, right? Oops, what happened? 3 times you add 2, then you will be at 11. So you were at, here's your mean, you were at 5, right? You went up 1 standard deviation, you got to 7. You went up another standard deviation, you got to 9. You went up another standard deviation, you got to 11. So 11 is 3 standard deviations above the mean, right? So that means its z-score is equal to 3. 1 standard deviation, 2 standard deviations, 3. All right? So yeah, I don't want to talk about this. Don't even look at that. I meant to delete that. Let's do this with a general example. What if we had something like 12, right? We have the mean of 5 and a standard deviation of 2. What would be the z-score for 12? Well, we know right off the bat, even just looking back, if we go another standard deviation, we're going to be up at 13. So 12 isn't going to be on a standard deviation boundary. It's going to be halfway in between. But we can figure this out using some algebra, okay? So we're going to use our variable z to be the number of standard deviations from the mean, and that is the definition of a z-score. And so we're going to say 12 equals my mean plus how many times do we have to add 2? Solving this equation by subtracting 5 from either side tells me 7 equals z times 2. Dividing both sides by 2, z equals 3.5. So 12 is 3.5 standard deviations above the mean. That's supposed to say above. Boy, am I typing this bad today. I don't know what's going on. Above the mean, okay? What if we didn't have all these values, right? We just had some generic mean u and some standard deviation represented by sigma. What would be the z-score? We can still do some algebra to figure this out. We have our formula because we know this data value is going to be equal to the mean plus some number of standard deviations times the standard deviation, right? That's exactly what we did last time. If we solve this equation for z, that will give us exactly our equation for z. So we're going to solve this. I know that if you took Math 95, you practiced solving these types of equations. First, we're going to subtract mu from either side of the equation. That gives me x minus mu equals z times sigma. Divide each by sigma. And we get z equals x minus mu divided by sigma, which makes sense because this top part is the distance it is from the mean. And then we want to divide that into units of standard deviation. So we divide it by standard deviation to see how many standard deviations are in that length. Regardless, you need to write this down in your notes because this is your formula for z-score. All right, so let's do an example. What is the z-score of x when x equals 1 and your normal distribution is distributed normal with a mean of 12 and a standard deviation of 3? Plug it into the formula. Z equals x minus mu over sigma. X is 1. 12 is my mu. Divide by my standard deviation of 3. That's going to be negative 11 over 3, which gives me negative 3.67. So this tells me that the z-score, that the value is 1, is 3.6 standard deviations to the left of the mean, right? It's negative. We went down 3 2/3 standard deviations. All right, I would like you guys to pause the video and try this example. I'll read it to you, and then I want you to try to fill in the blanks below. So some doctors believe that a person can lose 5 pounds on the average in a month by reducing his or her fat intake and by exercising consistently. Suppose weight loss has a normal distribution. Let X equal the amount of weight lost in pounds by a person in a month. Use a standard deviation of 2 pounds. So X is distributed normal, mu 2, sigma 2. Mu is equal to 5, sigma is equal to 2. Fill in the blanks. Pause the video, give this a try. All right, are you back? All right, so suppose a person lost 10 pounds in a month. That's my data value, X equals 10. The z-score for 10 is equal to 2.5. Let's make sure this is true. So my X value was 10 minus mu, which is 5, divided by 2, which is sigma. That's 5 halves, which is 2.5. The z-score tells you that X equals 10 is 2.5 standard deviations to the right of the mean, which was 5. What is the mean? That's what I want you to put in there. So it's 2.5 standard deviations above the mean, all right? So why do we use z-scores? Just to give us an idea of how far away our data value is from the mean. Is it pretty common within a standard deviation? Is it less common within 2, or very uncommon, maybe more than 4 standard deviations? All right, that's all I have for this section.